stands up, she organizes, she doesn't avoid hard work and hard conversations. I'm so lucky to know Marissa. I stand in awe of her. We are also lucky that we get to say we knew her when. And without further ado, I'm gonna let Dr. Marissa Loving treat you all to a fantastic talk.
Well, now that I'm like almost in tears from Michelle's lovely introduction, let me tell you a little bit about my math. So I'm actually gonna talk about one of the areas of mathematics that Michelle mentioned, which is these sort of length spectral results. And so let's go ahead and get started. So my sort of big picture motivating question is like this very classical question that Mark Kac asked, which is, can you hear the shape of a drum, right? If you just hear, like someone pounds a drum and you just hear the sound of it, do you know sort of what the shape is? And of course, this is sort of a very untechnical question, which has really a very sort of technical, deeper meaning if we want to make a sort of precise mathematical statement. And so the sort of more precise question here is, can you determine a planar region by the eigenvalues of its Laplacian? Okay, so you might be confused because Michelle just said I'm a topologist, and this sounds like geometric analysis. Okay, so instead of focusing too much on this motivating question, I want to instead turn to the motivating answer, which brings in the sort of area that I like to focus on. So this is a theorem of Tsunada from the 80s, which tells us that in fact, the answer to this question of Mark Kac is no, right? So I'm gonna sort of, this is a more general result, but I'm gonna restrict it to the setting of hyperbolic surfaces. And it says that in fact, there exists pairs of hyperbolic surfaces, which are isospectral with respect to both their Laplacian and something called their unmarked length spectra, but which are not isometric. So these sort of two pieces of data are not enough to tell you whether or not your surfaces have the same hyperbolic metric on them. Okay, so surfaces, right? There's lots of words in that motivating answer that I didn't unpack, but I'm going to start by sort of focusing in on my setting, which is surfaces. So in particular, I'm going to think about surfaces which are closed. Okay, so I don't want to have any punctures or any boundary components. I want to think about things which are finite type. Okay, so Michelle mentioned I think about also big mapping class groups, but for now I want to restrict to surfaces which have finitely generated fundamental group. Another way to think about this for closed surfaces is that they just have finitely much genus. Okay, so if you sort of look at this list, right, we have the sphere, which is genus 0, the torus, which is genus 1, genus 2, genus 3, and you can sort of just keep going as long as you always sort of have some natural number. Okay, and in order to think about these as hyperbolic surfaces, I'm going to actually restrict to the case of genus greater than or equal to 2. So I'm really going to be sort of looking at things like this or with more genus. Okay, so let's keep unpacking. What do I mean by a hyperbolic surface? Okay, so when I say hyperbolic surface, now I'm suddenly turning myself from a topologist into a geometer. And so what I mean is I'm going to think about my surface now equipped with a specific metric. In this case, sort of this hyperbolic metric. And so just to give you sort of a feeling of what I mean is, right, nothing about the topology of my surface changes, right? These all have genus 2, but sort of the shape of my surface changes. So if I look at, for example, this sort of same separating curve alpha, right, it's topologically the same on all my surfaces, but with the different metrics, it's going to have different lengths, right? So on this surface, right, I sort of have this metric where I get this long stretched out bottleneck. And so I look at sort of my curve here at the shortest part, right? That's the geodesic representative of my curve. Whereas here, even if I try to sort of find the shortest place for this curve alpha to go, it still can't get that small. It still has to be sort of big because of the way my surface is shaped. And so I can think about sort of comparing the length of this curve alpha in my different hyperbolic metrics, right? So it's sort of shortest in M2, right, over here, and it's longest in M3 over here. Okay, so this is sort of my now sort of geometric setting. And so let's turn back now to unpack this other part of my motivating answer, this talk about this unmarked length spectrum. Okay, so when I'm talking about the length spectrum, I'm talking about looking at the lengths of curves in my surface. And I want to do this in sort of two different ways, marked versus unmarked. Okay, so when I think about sort of the marked length spectrum, I'm thinking about the set of all the curves on my surface along with their lengths. Okay, so another way of thinking of that is instead of just having sort of a list of numbers, I sort of have pairs where I have the curve and then the length of the curve and the length of the curve. So I sort of know where this length is coming from. Whereas for the unmarked thing, I'm sort of forgetting about where my lengths come from, and I'm just keeping track of this sort of multi-set of curve lengths. Okay, so I don't have any sort of curve data. Okay, so these are sort of the two different ways that I'm going to think about toggling this length spectrum. And right now I'm thinking about the set of all closed curves on my surface. I'm not restricting to sort of any smaller subset. Okay, so here's my motivating answer. Okay, so let's sort of talk then about this spectral exiguity. So now we have from Tsunada's result that in fact hyperbolic surfaces are not unmarked spectrally rigid, right? Like we can have the same unmarked length spectra but still be isometric, right? So even though be non-isometric. So even though they have the same set of lengths, they don't actually have the same hyperbolic metric. Okay, so they don't have this type of rigidity. But it turns out that they are marked spectrally rigid. Okay, so this is actually like a very classical result of Fricka, which says not only are hyperbolic surfaces sort of marked spectrally rigid, but we can do so with a finite collection of curves. So a sort of cute statement of this result is something called the 9G minus 9 theorem, that tells us, in fact, to determine the hyperbolic metric on a surface of genus G of genus 2 or greater, we only need 9G minus 9 simple closed curves, right? So we went from having sort of this giant unmarked length spectrum, which was not enough to tell us what the metric was on our surface, to having this finite set of marked simple closed curves, which does. Okay, so for the case of the genus 2 surface, we just need 9 curves. And I'm going to show you what those curves are. If you're familiar with thinking about sort of the Teichmuller space of a surface, you might see why this set of curves could determine your metric. But it's totally okay if you're not, it's still a cool picture. So we're going to start off with these 3 red curves, which give us a Pantz decomposition of our surface. So this is where the sort of 3G minus 3 comes from in the 9G minus 9 theorem. And then we're going to take a set of sort of transverse curves. So these are curves which sort of are transversely intersecting all of our Pantz curves sort of minimally. Okay, so these are my blue curves. And then I'm just going to take another set of 3 curves, right? So here's my sort of third 3G minus 3, which is all of these curves, the blue curves twisted about the red curves. Okay, so again, if you sort of think about, if you're familiar with Teichmuller space, these are really giving us sort of the Frenchel-Nielsen coordinates, right? It's telling us sort of how to twist and glue back our Pantz on our surface. Okay, so this is the 9G minus 9 theorem. So what do we have going on sort of in between these two pictures of like extremely rigid and like not rigid enough? Okay, so yeah, so here's my sort of formalized question, right? Are hyperbolic metrics on surfaces determined by their marked or unmarked length spectrum? And we have now our answers, right? Yes, in the case of marked, no in the case of Tsunada. But what I want to now sort of modify this question to ask is, well, maybe we can find some sort of in-between spot for this rigidity. Maybe if we look at the unmarked length spectrum, but for a smaller set of curves that we understand better, such as the simple curves on my surface, so these are the curves which don't have any self-crossings, maybe this could determine our hyperbolic metric on our surface. Okay, so of course, you might say, what about Tsunada's result, right? We already have, Tsunada's construction is actually sort of very robust. The way that it works is you sort of take a surface, you put a hyperbolic metric on it, you choose some finite subgroups, we'll get to that a bit later, and you produce 2 covers of your surface, which have the metric that is induced by the metric on your base surface under those covering maps. And this is sort of how you sort of build up these pairs, which have sort of the same length spectra, but have different hyperbolic metrics. And you might say, like, okay, maybe that construction can actually produce a negative answer to this question if we just were a little bit more careful. Like maybe Tsunada's result is sort of already giving us that these sets of non-isometric surfaces have the same simple length spectrum. Maybe Tsunada wasn't just, maybe he wasn't keeping track of what was simple and what wasn't. So that's sort of the first thought that I had with my collaborators when we started working on this project. And it turns out that I was not the only person who had thought of this. So this is a theorem of Rasamate Manchung, who showed that in fact, Tsunada's construction can't do that. You can't just sort of be more careful and sort of keep track of more data and automatically get things that are unmarked simple length isospectral and non-isometric. So Tsunada's construction does not generically produce non-isometric surfaces with the same unmarked simple length spectra, okay? Which means that it's reasonable to hope that maybe the answer to this question is yes, okay? And so sort of as an initial goal, I would like to show that any pair of Tsunada's isospectral hyperbolic surfaces, which are unmarked simple length isospectral, actually have to be isometric. Okay, and so this is sort of the driving question behind sort of this piece of my research program, is trying to show that this is true. Okay, let's see how I'm doing. Yep. So some inspiration. So I want to go back and talk a little bit more about that film of Wasame. And so here's the sort of setup for understanding Tsunada's construction. Okay, so what we're going to do is we're going to look at a sort of this surface, a genus 2 surface. I'm going to call it M0, and I'm going to construct a surjective homomorphism from the fundamental group of my surface to this finite group G. Okay, and what I want to do is I want to take two almost conjugate subgroups. Okay, so these are subgroups where if you look at sort of every conjugacy class in your group and you look at the intersection with these subgroups, they always have the same cardinality. Okay, and what I want to do is now that I have these subgroups of my finite group G, I can pull them back under this surjection to subgroups of my fundamental group, right? And we have our nice like Galois correspondence for covers that if you have these subgroups of your fundamental group of your base surface, this gives you covers. Right? So now that's why I'm naming these MH and MK, because these are just the covers that correspond to those subgroups of my fundamental, well, subgroups of my finite group that I pull back to subgroups of my fundamental group. Okay, so here's the more technical statement of what Mangchai actually proved. Okay, so he proved like in this specific setting for a genus 2 surface, okay, if we have he actually, this is like sort of can be made extremely explicit. He picked a specific finite subgroup, G, and he picked two specific almost conjugate subgroups and showed that for almost every hyperbolic metric on the base subsurface, right, the induced metrics on the top surface were not unmarked simple length isospectral, okay? So this doesn't break our sort of goal, our claim. And so I want to just talk for a little bit is sort of the idea of the proof, right? So the proof strategy here is sort of two parts, okay? The first part is to find a curve gamma in M so that we have the following. We have that it lifts to simple curves with no self-intersections on one cover, but lifts to non-simple curves on the other. So what we're doing here is we're introducing some potential discrepancy into this simple length spectra, okay? But of course, right, having this is not quite enough because maybe there's some other curve on M0 that sort of lifts the other way, right? That lifts simply to MH, but does not lift simply to MK and sort of fills in those holes that we just made in the simple length spectra. So the key to making sure that you actually don't have sort of some sneaky other curve that sort of comes and says like, no, don't worry about gamma, I'm filling in the place, is you have to make sure that that curve gamma that you pick doesn't have length twins. So there isn't another curve on S, which the lifts will sort of fill in the gaps. And so this is sort of the way that the proof works. It's sort of a two-piece thing. And Wasame does this very constructively. Right, so he picks actually an explicit curve, and instead of sort of showing here, like he actually shows that it has no length twin, like computationally. Like he goes and he checks every potential curve and is like, no, there's nothing that can take the place. And this is how his paper goes. It's really a really cool paper and was like really intimidating to read because it used so explicitly all these things that we sort of learn about covers, which turns out are really hard in practice to understand. So I think this is a really, really cool paper that ends up being, even though it's a sort of very general result, is very constructive. So our hope is to use this as a potential strategy to understand sort of the more general setting of any pair of Tsunada isospectral covers, not just in sort of this specific setting with this specific group and this sort of genus 2 base surface. And so sort of the narrowed down goal then would be to show that if we have these two covers, right, which aren't equivalent as covers of M naught, right, they're not sort of isomorphic covers, then there's actually a curve on our base surface that admits a different number of simple elevations to one of our covers and not the others. Here we're introducing this discrepancy. Okay. So just for a moment, I want to make sure I tell you what I mean by elevations. Okay, so probably many people have thought about it, what it means to sort of lift curves to covers, like in like algebraic topology class. And often you think about this thing like that's path lifting, right? You sort of take a curve and maybe it like opens up to like a segment on your cover. So what I want to do here is I want to take only connected components of that pre-image on my cover, because I actually want to get things upstairs that aren't just paths. I want things that are actually closed curves. And so that's all I'm doing when I say I'm taking an elevation, right? I'm taking something so that it projects, this is a curve upstairs, which projects maybe to a power of my curve downstairs, right? So like an example of this would be if I look at like this curve here, this alpha, this is in my cover. So this is like alpha cubed, right? This projects to like alpha cubed downstairs, right? I actually have to run across many segments to get sort of downstairs. And so that's what I mean by an elevation. If I just took a path lift, I just get this segment here. So I don't want that. I want an actual closed curve. Okay. So sometimes I say lifts, but really what I'm always meaning is these sort of simple closed curves in the pre-image. Okay, so here's a first try. So this, I should have mentioned at the beginning that all of this work is sort of joint with Tarek Algab, Maxi Lon, and Sunny Zhao, and Nick Miller in some set of configurations. And so this first result is together with Tarek, Maxi, and Sunny. And we show sort of this first step, that if we have two covers of our surface S, these are regular covers, okay? So that's a really nice thing. So you can think of the fundamental groups of those covers sit normally in the fundamental group of your base surface. This gives you a lot of control about sort of what happens to simple closed curves on the cover, which is nice. And we have this sort of condition that I've highlighted in blue, that if we have any closed curve gamma on S, then there exists a simple elevation of gamma to X if and only if we also admit a simple elevation of gamma to Y. So we have we're forcing some type of correspondence between the simple curves on each of our covers. And it turns out that if you have this, then you have that your covers are the same. They're actually isomorphic covers, okay? If you have isomorphic covers, then, yeah, so they're actually isometric. Okay, so here I just want to point out that this maybe feels like a bit of a mouthful, this sort of, this condition that I've highlighted in blue, but this is really just sort of reformulating what we wanted to show before, right? This is exactly saying, right, what did we want to show before? We wanted to show that if we had things which weren't equivalent as covers, then they admitted different number of simple elevations. And so now we're saying if they admit the same set of simple elevations, then they actually have to be the same. Okay, so we're sort of making progress towards our goal here. But I did say this is a first try, which is a little bit of a giveaway that maybe this is not sort of getting us where we need to be. And it turns out that regular covers are very nice. And Tsunada covers aren't regular. Because in that setting, we're always looking at these covers whose fundamental groups are sitting as almost conjugate subgroups, which are not conjugate in the fundamental group of the base. And it turns out that almost conjugate subgroups that are not conjugate will never give you regular covers. Because as soon as you have regularity, being almost conjugate actually gives you conjugacy. They're actually conjugate. So even though this is a cool, like a sort of cool statement that allows us to characterize covers in this sort of really nice way, just understanding the way curves are lifting simply, it doesn't really get us any closer to this sort of geometric statement, understanding this sort of length spectra. And so this brings us to our second try, Okay, so this is joint again. So this is with Tarek and Maxi again, but now we also have Nick Miller joining us. And we showed that we can sort of give the exact same statement, but drop the condition of regularity. Okay, and I do want to point out, in case my referee is in the audience, that the referee of the first paper was like, oh, couldn't you just like very easily do this like little thing and like drop the regularity? And it turns out that no, like not only did our proof of, in the first case, we could show that it really required regularity, but it wasn't just that we were somehow not slick enough to like beef it up to something that gives us sort of a statement for non-regular covers. The proof of this is like very different. Okay, so we do some, I don't have time to get into the proof here, but it sort of really, it's really beautiful because it uses this interplay between these sort of two geometric objects that we can naturally associate to a surface. One of them is sort of a coarse geometric object called the curve complex. And one of them is sort of like a very geometric object called Teichmuller space. And it turns out that you get a really nice interplay between the boundaries of it at infinity of these two objects. And you can leverage that to make sort of take this combinatorial data about curves on your surface and turn it into like really rigid geometric data about what types of covers you have. Okay. So possible strategy. We come back to our possible strategy, right? This was sort of our strategy. Of course, so far we've been focusing on this part, right? This sort of one to show, and I've sort of been ignoring this asterisk, right? This sort of fact that we actually need something that's sort of uniquely sitting in the length spectra downstairs. It doesn't have sort of another curve with the same length, right? So this is sort of important. I know I kept it small, but this is an important thing. And so what I want to just end with is sort of a statement that ties together this characterization of covers with this idea of having this sort of isolated curve in our length spectra. So this is a theorem of myself, again, with Tarek, Maxi, and Nick. And we show that these sort of two pieces of data actually are enough to like give us this sort of simple length spectrality statements. So it says that if we have a curve on our surface, which doesn't have length twins on our surface, and which admits sort of different number of simple elevations to each of our covers. So again, this is sort of using the contrapositive of that statement we are making characterizing our covers. Then we get that these two covers are not generically simple length isospectral over S. Okay, so that means that so almost any choice of hyperbolic metric on our surface S, you're not going to get sort of that they have the same simple length spectra. Okay. And because of like sort of the way the construction goes from Tsunada, they're also not isometric, right? So we're sort of like distinguishing from their hyperbolic metrics. Okay, so I think I have a few more minutes on my timer. So I want to change pace just a little bit and talk about sort of what it's like for me as a non-white woman to be in a space like the AWM. So some of the folks here I went to grad school with and will know that I did not find a space for myself in the AWM chapter at my graduate school. I remember I had a really, really hard time at the beginning of graduate school. It was a big transition for me. As Michelle mentioned, I did my undergrad at the University of Hawaii at Hilo, and it's also where I grew up. And it was a big transition moving to the middle of Illinois, Urbana-Champaign, and moving into a department that was overwhelmingly white. And by overwhelmingly white, I mean I was one of the few only like visibly non-white women in my graduate program. And I remember my first year, my first semester, I was like, I really didn't want to go to the AWM because I thought of it as like a sort of last resort. I was like, you know, if I can just sort of keep going, that will be the space that I go to like when I'm at my wit's end. Because there, right, that's where people are supposed to like care for me. That's where people are supposed to be thinking more about what our experience is and not just like what mathematics we're producing. And so my first semester was a disaster. It was awful. And at the end of the semester, there was an event that they called the Wine and Wine. And it was at one of the older graduate students' houses. And I remember going there and talking about some of the experiences that I'd been having with my peers during my first semester. For example, I had lots of my white male colleagues who would tell me that, like, I only got into grad school because I was a woman of color. I only got the NSF grad fellowship because I was a woman of color. They would have gotten it if they weren't white men. And I was trying to explain how this felt to some of the other women who were there. And I remember one of them just talking over me, like cutting, like just literally talking, interrupting me and being like, no, Marissa, that's not because you're brown. That's just because you're a woman. And that is my experience with AWM. And I want to just emphasize that spaces which support white women while excluding or harming Black, Indigenous, and Latina women and other gender minorities are not free of sexism and misogyny. There is no way to separate my race from my gender. This is another thing that I've heard when I say that this professor has treated me in a sexist way. Oh, but he has white women students, so he can't be sexist. So my womanhood just goes out the window, right? What does that mean? I think this is something that is pretty crucial to be thinking about more closely as we sort of put together these spaces and make sure that there are places that people like me want to be in, that we feel we're included in. And I think in the same way that we should also think about the way that we use womanhood and try to separate it from other folks who are marginalized along axes of gender to put forward and uphold white supremacy. I also wanted to mention that I was troubled to see the NSA table that is right outside this door. And I wanted to share this excerpt from a statement called Mathematics Beyond Secrecy and Surveillance that the Just Mathematics Collective put out recently. And I'm going to read it out loud. It says, there can be no good argument that the NSA is good for mathematics without completely throwing under the bus anyone for whom being part of a national mathematics community is out of the question due to outrageously oppressive circumstances, including those exacerbated by security agencies. I think this particularly resonates with me because it sort of reminds me of what it feels like to be in these spaces. That for me, right, there's no good space for me if it is predominantly predicated on being an inclusive space primarily for white women. So the Just Mathematics Collective statement it makes some calls on us as a community to think closely about what our ties with the NSA and other sort of security agencies are. I myself have signed on to their pledge to not be taking money from the NSA and other security agencies such as the Department of Defense, to not be writing letters for students who are going to be working for those types of agencies. And whether or not this is something which aligns with your own personal values, I think this is something that you should actually check if it aligns with your own personal values, and to really spend time thinking about what it means for the mathematics community to be so deeply entangled with agencies which promote horrible abuse, specifically focused on people who are most marginalized in this country. Thanks.
In the explanation of the proof, you said, okay, pick a curve that is not a length twin. What if there are no curves like that? What if every curve in your metric, or every geodesic curve in your metric has another curve that's the same length?
This is an excellent question. So we are in the process of writing a paper about this result and sort of more of the applications to sort of length spectra questions. This was a paper that I was like, oh, it's definitely going to be out last fall before I apply for jobs. And then I was like, it will definitely be out before the end of the semester. And now I'm like, it will definitely be out by the end of the summer. But in it, one of the things that we do is that we are constructing sort of families of examples where we can actually produce curves which don't have length twins. But it really is important, is actually demonstrating that either there always exists a length twin or like saying when there is one. So that, yeah, that's not, I don't think that any question is a silly question to be asking. But in particular, that's an excellent question because it really points towards what we've been focusing on recently.
I'm wondering if you can say a little bit more about almost conjugate subgroups. What does that mean and what do we know about them?
Yeah, so for me, this is all that almost conjugate subgroups mean, is my little definition, right? It's just things which are sort of close to conjugate, but not conjugate on the nose. The really important characteristic is the fact that if you're normal, almost conjugate applies conjugate. Once you have sort of conjugacy, right, then you are, right, if you have two subgroups of, so one of the ways, right, there's different ways to think about covers. One of the ways that you can think about covers is thinking about sort of representations of your, or like metrics is thinking about like representations of your fundamental group into PSL2R. And so when you're thinking about then covers and you're thinking about like whether the metrics like are the same, you can think about those representations into PSL2R. And so once you have things which are conjugate, those actually are giving you the same cover. Those are isomorphic covers. And so once we get, like in the case that we're restricting to things that are regular, we sort of can't, we don't have anything to say anymore. Because it's not the setting that we're looking at, right? It's not where we're actually producing these sort of isospectral but non-isometric surfaces.
Is almost conjugate related to like virtually conjugate, having finite index subgroups which are conjugate?
Well, the thing is, this is a condition in a finite group. So like, yeah, everything is finite index, but like sillily.
Well, so firstly, I just wanted to thank you for sharing your experiences. I know that's like a really hard thing to do. So I just wanted to echo that, like, I appreciate that. And I think that we all can do better in listening to the voices of people who are marginalized on different axes and like really making sure that we're making substantive changes to make our spaces inclusive to people, not just in the like gender majority here, but also for people who are marginalized along various axes, whether it's your race, your disability status, your orientation. Anyway, so thank you for that. And also I wanted to ask, so your result sort of sits in this like interpolation between like Tsunada's result that says like, okay, you're not spectrally rigid if you look at like this unmarked length spectra versus like maybe you are spectrally rigid. I forget the author of the other result.
Oh, Fricka, yeah.
Yeah, you are spectrally rigid if you sort of include the marked length spectra. Do you think there might be other results sort of along your axes that like?
Yeah, that's a great question. So there are lots and lots of results about sort of spectral rigidity. I did not focus on them because it's only such a short talk. But like there's lots of people who study this from a much more like geometric perspective. So there's results about like non-positively curved Riemannian metrics. There's results about negatively curved Riemannian metrics. There's results about a flat metric. So I have some results thinking about certain flat metrics. There's results where when you really start to like think more carefully about like what subsets of geodesics that you have. Noelle Sawyer was here yesterday who gave a talk. She considers these sort of length spectral rigidity results for sort of more restricted types of geodesics. And there's sort of like all sorts of cool tools that you can use in those settings. So like something that people use a lot to sort of understand these sort of different types of metrics and their rigidity is like looking at sets of geodesics in like the universal cover and thinking about things called geodesic currents. And so there's people here who know about these things and do things with that. So yeah, there's sort of lots and lots of different flavors. It's not so much as much interpolating in this hyperbolic setting. I don't think there's anything other than what we're thinking about right now. But when you start looking at other types of metrics, then certainly there's sort of lots of different ways that you can restrict either sort of being marked or unmarked, or sort of what your set of geodesics are, and like what is the minimal set of geodesics that you need to like gives you rigidity.
Hi, so Marissa, I just want to also thank you for sharing your very personal experiences and bringing these topics up in this forum. I know it's not easy to do, and I admire your bravery. So also, I'm very proud that you mentioned Noelle, and she is a graduate of Wesleyan University, of which I'm currently the chair of mathematics and computer science there. So thank you also for that, and thank you for your wonderful talk.
Thank you. Yes, if you don't know Noelle, you should, because she's basically the best ever.
Okay, I think maybe that is a good note on which to end. So let's thank Marissa again for a terrific talk.